Hey YouTubers, it's Martin Shkreli. I'm back after about a month hiatus to do chapter 14 of the Zumdahl and Zumdahl 9th edition. This chapter is Acids and Bases. It's pretty dense. It's probably the most dense chapter in the book, and I think it's pretty important, so we're going to go through it in great detail. I spent the last month, at least for educational reasons, or educational part of my life, I was on Khan Academy of all things, and I highly recommend that website. I can't recommend it enough. I think you guys probably saw me doing a lot of the math section of Khan Academy, and I fell into that rabbit hole. So anyway, you can see that the cover for this PowerPoint, which is the way I'm doing these lessons now, is Arrhenius, who is the father of chemistry, in my opinion. He's sort of our Newton, or physics is Einstein, and Einstein or Newton. And we're going to talk about, his name comes up quite a bit in acids and bases. So I thought I'm really enjoying showing off this graphic that Excel made for me, really. PowerPoint made for me. So anyway, what are we going to talk about? Let's talk about all the definitions of acids and bases, of which there are three. We're going to use what we did in the last lesson to talk about acid-base chemical equilibria. We're going to talk about strong and weak acids and bases. We're going to calculate using the pH scale, so you can finally tell all your friends exactly what pH is. And if you're like me, you may forget it, but hopefully you'll remember. We're going to talk about polyprotic acids, and then salts, and then finally the Lewis model, which is just one of the three definitions of acids and bases. Hey everyone. All right, so let's start with the overview, and I'm on page 652 and 653, so if you're following along in this wonderful book, the Zumdahl and Zumdahl 9th edition chemistry textbook, which is a introduction to chemistry. It's sort of a either gifted high school or college, early college kind of chemistry course, corresponds to maybe chemistry 101. And we don't assume any advanced knowledge of math, although we will be using logarithms and the quadratic formula in this chapter. So this is probably the most math heavy that chemistry gets, at least with respect to this course. Okay, so Arrhenius, our hero, who, again, I would encourage you to look up his life. He really was a model citizen and scientist. He had this theory that acids, or his definition is that acids produce hydrogen ions, or protons, in aqueous solutions, and bases produce hydroxide ions. And this is sort of the way I think a lot of us think of acids and bases, but it's not exactly the perfect definition, because there are, of course, non-aqueous solutions. Water is not the only solvent. And there are bases that are not just hydroxide donors. But the hydrogen ion part is about right. I mean, basically, protons, something that furnishes protons is generally thought of as an acid. Although, when we talk about the Lewis definition, we'll think about that even further. Maybe that's not even ideal in and of itself. So the Bronsted-Lowry model improved on this a little bit, but just saying that acids are proton donors and bases are proton acceptors. They don't have to necessarily produce hydroxide ions. So we look at hydrochloric acid, which is sort of our de facto definitive acid. When that's dissolved in water, each hydrochloric acid molecule donates a proton to the water molecule, and that's a little confusing, I think, to the amateur chemist. I think we all accept this idea that you have this hydrochloric acid, and they sort of come apart, they dissociate. You have the proton, and then you have the octet chlorine that's satisfied, and then you have that loose proton. But what ends up happening that's a little bit different is that hydrochloric acid, the proton, is donated to water. And so what ends up happening is of course the hydrochloric acid is an acid, but the water is actually a Bronsted-Lowry base, which I think is a pretty complex idea. And if you just sort of take that as a given, and you can think about it, maybe at some point when you have more time, as it's really a fascinating concept. What ends up happening is, how does that proton fit on that water? Well, we all know water's H2O, and it's electrically neutral. So how does that work? Well, it becomes an ion. We call that ion hydronium, and this is a pretty complex concept. But let's take it for granted that it's this H3O plus ion, and so one of oxygen's unshared electron pairs is sort of involved in this proton acceptance. So think that through, and might start to make sense. So when we think about an acid and dissolving in water, this is a pretty important and dense terminology that you're going to have to become acquainted with. We think of the acid as this sort of HA, this general A, could be any other, generally it's going to be an anion. So it could be hydrofluoric acid, hydrochloric acid, it could be sulfuric acid, but that A is going to be part of it. You're always going to have an H in an acid, right? So when we put it in an aqueous solution, the base will be this Bronsted-Lowry base of water. And then what ends up happening is they sort of flip in definition. So you have this conjugate acid, this hydronium is a conjugate acid. Why is it a conjugate acid? Well, you can see it's positively charged, right? So it now becomes a proton donor. So it's the acid now. It kind of is that like that movie Captain Phillips when he says, "I'm the captain now." Well, water starts as the base, and then when it grabs that proton, now it's the acid. And the opposite holds true for the acid. The acid has given up its proton, it's negatively charged, so now it's the conjugate base. So spend some time thinking about that. It definitely could hurt your brain if you don't exactly understand it. All right, moving on a little bit. I recapitulated that whole idea, and maybe I'll explain it a little bit more. Water is polar. We learned that a long time ago. It has these dipole moments. And the water pulls that proton from the acid. And that's a really important concept to understand. You know, when you have that hydrochloric acid, again, you can envision this small hydrogen atom bonded to this big chlorine atom, and it doesn't dissociate by accident. The water has to pull that proton off of that acid, and this is a really important concept. Oxygen has that partial dipole moment, right? So it's going to be pulling that hydrogen. Oxygen is so electronegative, it's got these lone pair electrons, and it wants that proton, so it's going to pull it off. So the conjugated base, right, is this deprotonated acid. So think about that chlorine again. You know, it's deprotonated. Its hydrogen has been ripped off of it, in essence, by the water, by that dipole moment. The conjugate acid is a protonated water. So it's been protonated, a proton has been added to it. And this word protonated will come up again and again and again. And in medicinal chemistry, organic chemistry, when we talk about protonated species, this is going to be really important in drug development, which is why we're talking about this in the first place. Okay, so the next sort of governing dynamic that it makes sense for you to sort of spend some time on is this idea that there's competition for that proton. So you have that acid, and think again about that hydrochloric acid. That's the best way to think about it. And it dissociates. There's competition for the proton. That proton, remember the chlorine's fine. The chlorine's sort of there. And it's, you know, they're both ions, so they're both interested in getting that proton back. So there's a competition between the conjugate base. You have this chlorine, it's sitting there, it wants the proton because it's an ion, right? It wants the proton. But at the same time, the water wants the proton because of its dipole moment. So the interesting thing is this competition for that proton is between these two bases. And if the water is stronger base than the deprotonated acid, the conjugate base, then the equilibrium position will be far to the right. So all of that ionization will take place. The water will rip off the protons off of the acid. And we'll talk about what happens in the other case, where the stronger base is actually not the water, but it's the conjugate base. In that case, what ends up happening is the acid won't dissociate, and we'll call that a weak acid. So let's look at that in a second. So here's the formula, and this looks pretty familiar to maybe your chapter 13 formula, if you want to flip back and look at the law of mass action and equilibrium constants. This is very similar. Instead of calling it a general equilibrium constant, we'll call this Ka. And this Ka value is going to be really important. And we're going to talk about pKa and all those things over time. So the Ka we'll define as this hydronium ion multiplied by the protonated acid all over the acid. And this is the acid dissociation constant. So it's in essence going to be protons multiplied by the protonated acid over the acid. That's the dissociation constant. So what are the dissociation reactions for these? We have hydrochloric acid, acetic acid, and ammonium. I'm reading from the 9th edition of Zumdahl, if there's any confusion. Okay, so here we have hydrochloric acid dissociating into the proton and chlorine, and then same thing for the following two. So we understand what the dissociation reactions look like. It's pretty simple. So how do we use that? Well, the concept of acid strength is where this will come in handy. So the strength of an acid is the equilibrium position of the dissociation reaction. So how much will it dissociate? So a strong acid is where it lies far to the right. So all of the acid is ionized at equilibrium. So this is the equilibrium, right? This is at equilibrium is what we're interested in. So a strong acid will yield a very weak conjugate base. So the water will win this competition. So let's go back here and look at this. So a strong acid will yield a weak conjugate base. The weak conjugate base will lose the competition. For that proton. Water will win it. So that's a really important concept. A weak acid is the opposite, where the equilibrium position lies far to the left. So in this case, a weak acid, you're going to have the equilibrium position, so there's less dissociation. The water, in fact, will lose the competition for the proton, and in fact, the conjugate base will win it, and therefore the acid will not dissociate as much. And that makes sense. It's a weak acid. There's less protons swimming around. So strong acids, we have the sulfuric acid and hydrochloric acid. These are the strongest acids that I think we talk about. And then we have weak acids, of which there are many. So finally, I'll mention organic acids that have the COOH group. These are usually very weak acids like acetic acid and others. Those are the carboxyl function group. All right, so let's talk more about acid strength. The strongest acids, interestingly, you can't measure their Ka. So let's look at this for a second and think about a really strong acid and wonder why that is. Well, if you think about it, the Ka is so close to 1 that it's impossible to measure it. The reactant, the denominator is so small relative to the numerator. So let's look at that one more time. So it's actually the amount at equilibrium. So think about that. They're close to 1 over here, but at equilibrium, the amount of undissociated acid, this won't equal 1. It'll actually be infinitesimally close to 0, the amount that's not dissociated. All of it will be dissociated because it's a strong acid. So these numbers will be close to the molar amount, but this number will be so close to 0 that it won't make sense. It'll be close to infinity. So I misspoke when I said 1. So just think about that. You can't measure the Ka of a truly strong acid because in the law of mass action, it's so small. The unionized acid in this case. Remember, it's the reactant on the bottom and the product on the top. We learned that in chapter 13. So here we have the Ka for a number of other acids where you can actually measure it. So we have chlorus, and we have hypochlorous, and etc. We have hyperchlorous and chlorite. So you can go through all of these. There's an extremely weak acid in cyanide, and sort of stronger and stronger acids over time. So let's look at a basic problem regarding acid strength. Let's arrange the following species in order of their strengths as bases. So here's water, here's fluoride, chloride, nitrite, and cyanide. So very simply, strong acids have weak bases. They correspond quite well. The strongest acids, HCl is the strongest. So Cl must be the weakest base. So Cl is going to be the weakest base. Water is stronger than strong acid conjugate bases, but weaker than weak acid conjugate bases. So we'll think about that, putting it here for now. In the inverse, we're going to have the weak acids, right? We'll have strong conjugate bases. So the strong conjugate bases will be here. So these are very strong bases. So that makes sense if you slow down and think about the idea of the inverse of the acid strength. So really weak acids will form really strong conjugate bases, and these are the bases. So here's the order. All right. Amphotericism. It's a big word, but it means something very simple. Water is amphoteric. It can behave either as an acid or a base, and this auto-ionization is going to be a really important concept for the rest of the rest of the lesson. So, two molecules of water can auto-ionize into hydronium and hydroxide, and there's a formal equilibrium, and here's the equilibrium sign that we learned last time, and you see the water becomes hydronium plus hydroxide, and law of mass action gives us this simple equilibrium. And what's interesting is that we have this ion product constant. You're going to have to really slow down and think about that. The ion product constant we'll call Kw, and here I'll just subscript this W. And this is the dissociation constant for water. And what it is it's actually 1.0 times 10 to the negative 7th molar at 25 degrees Celsius. And we have this masterpiece. And this is a really important concept in acid-base chemistry, where the dissociation constant is equal to the protons multiplied by the hydroxide ions. And what we get when we multiply these two things, if you know a little bit of algebra, is 1.0 times 10 to the negative 4th. So this is the ion product constant, or Kw for water. So this is what we'll get. We'll get this many 1.0 times 10 to the negative 7 hydrogen ions, or protons, and then 1.0 times 10 to the negative 7 hydroxide ions. And so when we multiply them, there's a constant, and this is going to come in really come in handy in a minute. So how do we interpret this? Well, basically in any aqueous solution, the product of protons and hydroxide ions must always equal 1.0 times 10 to the negative 14th. So when we have a neutral solution, they're equal, but an acidic solution, which I think we all understand, is when we have more protons than hydroxide, and vice versa for basic. And of course, one last little footnote here is that pH is going to be temperature dependent. So at a higher temperature, you're going to see a difference in the Kw. But let's not get distracted from the really important concept here that we must always equal 1.0 times 10 to the negative 14th. And this simple concept that water will dissociate into hydronium and hydroxide in this special value, it's going to be really powerful for us to solve some problems. So let's take a look at calculating the amount of ions for both protons and hydroxide ions. So let's do these problems. Calculate the values of I guess H plus and OH minus, hydroxide and protons, for the following solutions at 25 degrees Celsius, and determine if they are neutral, acidic, or basic. Okay. Well, here A, we have 1.0 times 10 to the negative 5th. We had a question here. What does auto-ionization mean? Let's go back real quick, and I just explained it. So water normally is not an ion, right? It is simply a neutrally charged molecule. But what water can do, some amount of water, very little amount, but some amount of water, it can be amphoteric and become a base or an acid. And it does this automatically, and that's what auto means. And ionize means it'll become charged particles. So water, two molecules of neutrally charged water, can spontaneously become hydronium, which is positively charged, and hydroxide, which is negatively charged. And this will exist in equilibrium. And the ion product constant equilibrium tells us how much of the ions we're going to see, which is 1.0 times 10 to the negative 4th per mole. So I hope that makes sense. All right, yeah, don't wash your hands with 6 molar hydrochloric acid. That would be, you may not have much hands left after that. So anyway, enough jokes. All right, so we're here to calculate the values of 1.0 times 10 to the negative 5th molar hydroxide ions. How many protons are there? And how many hydroxide ions are there? Hi, KDR. All right, so remember the Kw is always going to be 1.0 times 10 to the negative 14th. So solving for H plus is very easy since they're giving us the OH minus. So you can see that the H plus, I'm just going to highlight it here. Maybe I'll just move this out to make it easier to see. The H plus times or multiplied by the OH minus amount, which they're telling us is 1.0 times 10 to the negative 5th molar, is always going to equal 1.0 times 10 to the negative 14th molar. So all we have to do is we put our Khan Academy hat on and we divide this part by both sides, because we want to isolate, we're trying to solve the H plus amount. We know the OH minus amount, they told us that. So we divide this by both sides. When we do that, we're taking 1.0 times 10 to the negative 14th molar, divided by 1.0 times 10 to the negative 5th molar, and all we do here is we get, here it all is, that we get 1.0 times 10 to the negative 9th, because when you divide exponents, we simply subtract them, and we get 10 to the negative 9th molar. So we have, in this solution, we have 1.0 times 10 to the negative 5th molar hydroxide and 1.0 times 10 to the negative 9th molar protons, or hydrogen ions. And again, they add up to that special number, negative 14th, and that special number is going to be really important. And of course, since there are more OH ions than H plus ions, this is a basic solution. So, let me make sure my Discord is on. If you're in my Discord, you're welcome to ask questions. Alright, so we're going to do the same process here in the B, and what's interesting is that, again, since it has to equal 14, we're going to find very quickly using the same math, and we don't even have to do the math, but you can certainly jot it down if you'd like, we get that it's actually the same amount. We have 1.0 times 10 to the negative 7th molar hydroxide, we have 1.0 times 10 to the negative 7th molar protons, or hydrogen ions. So this is a neutral solution. Alright, so now we're going to do it a little tricky here. They're telling us the amount of protons, so we have to solve for the number of hydroxide ions. So we have 10.0 molar protons. It's a lot. And 10 molar of anything is a very concentrated solution. Alright, so we do the same process, except we have to divide both sides. Instead of dividing it by the hydroxide amount, we're dividing it by the proton amount. If we divide both sides, we're going to have 1.0 times 10 to the negative 14th molar divided by 10 molar. And 10 molar could also be expressed as what? 1 times 10 to the 1, right? So if we do that, 1.0 times 10 to the negative 14th divided by 10 is 1.0 times 10 to the negative 15th. So there are very, very, very few hydroxide ions and very, very, very many protons, and therefore it's acidic. And you think about that solution in your head, and I think you'll learn a little bit more about acids and bases. I think you'll understand it. So let's talk very quickly about autoionization of Le Chatelier's principle and that problem. So at 60 degrees Celsius, you can see the Kw is, let's see, I guess it's higher than at a lower temperature. So using Le Chatelier's principle, is the autoionization of water exothermic or endothermic? And let's calculate the ions of a neutral solution. So the Kw is increased due to the temperature change, right? It's gone from 1.0 times 10 to the negative 14th to 1.0 times 10 to the negative 13th. And this is a system which was previously at equilibrium, and it's being heated. It's being heated, so that this value, this Kw, has gone up. The system will adjust back to equilibrium by consuming the energy. So this is an endothermic. So it's taking in this energy. It's being heated. So it has to get back to equilibrium, and ultimately energy is a reactant. So the calculation is pretty simple. It's the square root of this number, because remember the two, when multiplied, OH minus and H plus, have to equal this Kw. So it's just 3 times 10 to the negative 7th instead of 1 times 10 to the negative 7th. So I hope that's clear. Le Chatelier's problem and principles are a bit esoteric, and I don't think that important, and pretty obvious, and we went over them last chapter, I believe. So let's talk about something a little more practical, which is the pH scale. So, little known fact, the pH means power of hydrogen. So the H plus is a very small number usually. It ranges anywhere from 1 to 10, 1 times 10 to the negative 14th. And it's easier to logarithmically express it as a logarithm. So the pH scale is a log scale that transforms solutions with base 10. So if you know a little bit about logarithms, you can do this pretty easily. So if we have H plus as 1.0 times 10 to the negative 7th molar, the pH is the negative log of that, so the pH would be 7. So this is a neutral solution. You might have heard pH of 7 is neutral. That's water, blood, pure water, right? Whereas some people like water that's a little more acidic, and in fact, if you really care about this, you can look up which water is more acidic than others. In fact, that might be fun. Let's do it right now. pH values of water, different bottled waters. That's fun. In fact, I went to a very fancy restaurant in Italy once, the first time I ever went on vacation in my life, and I went to the super super fancy restaurant, and they said, here is the pH of all the different kinds of waters we have. I mean, I've never been to a restaurant that tells you that. It's really, really impressive. And the bill was, the bill proved it. So let's see, the Dasani has a pH of 5.6. This is what I'm drinking now. It's called Nestle Pure Life. I actually don't like the taste that much. Its pH is 7.3, so it's a little basic. And then you have these, Evian is even more basic, it's 7.9. Fiji is a slightly basic, also like Nestle, it's 7.3. Poland Spring is 7.2. Arrowhead, which I think they serve a lot in Europe, or no, Aquafina is what they serve in Europe, is very acidic. Very acidic relative to other waters. So you can measure your own pH maybe of your tap water if you'd like. I don't know. Maybe we can look that up too. Maybe we can look that up too. New York City tap water pH. I wonder what it is. 7.2. So it's a little closer to the Nestle Pure Life. So anyway, that is basically a logarithmic way. And if you don't know logarithms, we can do them real quick here. So we can take -7, and 10 to the -7 is this, right? It's just 1 with the decimal shifted over 7 times. You can just count 1, 2, 3, 4, 5, 6, 7, 7 to the left. And if we do the logarithm, we take the negative number after the logarithm, we get 7. So pH is just the logarithm. It's an easier way to express a really small number, a really large number, as just -7. In this case, it's a negative number, so it's 7. So the smaller this number, the higher the pH. So 14, right, would be the amount of protons is 1 times 10 to the -14th. So the amount of OH ions, hydroxide ions, is the opposite. So remember, because they always have to equal that Kw. So pure acids have almost no hydroxide. So pure acids are close to 1. It's 1.0 times 10 to the 1. They're molar. So you have different pHs here, and you can see apples, Dr. Pepper soda is very acidic, Coke and Pepsi, very acidic, grapefruit and orange juice. And here's stuff you don't want to drink, like bleach, oven cleaner, hair straighteners, soapy water, ammonia, etc. So you can see that some of these cleaners are basic, soaps and so forth. And you think about tasting soap, that's what bases taste like in general. And if you think about drinking Coca-Cola or lemon juice, that's what acids taste like. So we all know that from just personal experience. So let's do a quick pH problem. This will be fun. And now the book, I found a typo. I was actually doing this lesson very vigorously, and then I found a typo. And the typo, for whatever reason, set my brain off into a manner where I didn't want to do the lesson anymore, but I went down Khan Academy road, just participating as a student in Khan Academy, but now I'm back into this mode of wanting to educate, but it frustrated me that there was this typo. But let's flip over to page 660. And I looked on the internet if there was a correction, but I couldn't find it. So in any event, enough of that. What is the pH and pOH, which is the power of hydroxide ions, similar to pH except just measuring pOH, for these solutions at 25 degrees Celsius? Well, the first one they give us is the solution of 1.0 times 10 to the -3rd molar hydroxide ion, and you simply might be able to figure this out in your head. So it's very easy. It's just 1.0 times 10 to the -11th. And the pH scale transforms that to what? To 11. To 11, because that's how the scale works. It's a negative log. So if you want to do it out in math, you could simply write 11, 10 to the -11. This calculator, it takes 10 to the x, you type the x in first, and it's this long number with 11 zeros before the 1, or 11 places, I should say, before the 1. And if we want to take the logarithm, it's a negative log, so we take the log and we add a negative sign and we get 11. pH is 11. And that's a very basic solution because there's so much hydroxide relative to protons. So here we have the opposite. The book has this terrible typo. Let's see, how do I do this? Well, B is I guess I skipped B, which is very easy. B is this, moment. B is 1.0 times 10 to the -7th molar hydroxide, which is simply very easy to calculate. The pH would be 10 to the negative 7th hydrogen ions or protons. So C is what we're dealing with where there's this typo. I just want to make sure the book corresponds to the book correctly. So C is where there's a typo. So here 1.0 molar protons, they want us to find out what is the pH and the POH. So that's the question. So the typo in the book, they try to solve it in the book, and it's all messed up, unfortunately. The OH is 1.0 times 10 to the negative 14th. So it's pretty simple. The pH is 0 and the POH is 14. But the frustrating part in the book is they give the wrong solution here. It's actually 10 molar hydrogen ions. So anyway, that was a little annoying to see, but if you calculate out the values, you'll get the answer as such. So let's move on to the next one, where we have some basic pH intuition. Ali K is correct here. pH plus POH is 14. This is intuitive and it's provable with a little bit of algebra. We use the anti-logs to reverse backwards from using this, and I won't belabor those too much, but it's pretty simple and intuitive. So let's talk a little bit more advanced work, talk about strong acids. So when we look at these strong acids like hydrochloric acid, we have to understand what are the major species of this solution. This is what the book always asks you to do as the first step, and they really like this kind of concept of listing the major species first, and I like it as well. And so the easiest way to do it is water will be the major species, of course, because it's an aqueous solution. And then we'll have protons and we'll have the chlorine ions. So why don't we have any OH ions? And what's interesting here is that the HCl will be completely dissociated. And what we won't have is any HCl. But why won't we have any OH ions? Well, think about that for a minute. And the interesting reason is that autoionization won't produce enough OH ions, and nor will it produce any meaningful H plus ions. So at the end of the day, what will happen is we'll be left with protons, chlorine ions, and water. So by listing these major species, we'll feel comfortable that we can calculate the equilibrium. So let's see how we can do that with this HNO3. So we have 1.1 molar HNO3, and then we have this very, very small 1.0 times 10 to the negative 10th molar hydrochloric acid. All right, so the major species for the first problem will be, of course, protons, the ion, and the negative ion, or the cation, or I'm sorry, the anion, and water. So the negative log of 0.1 molar of protons, which is how many protons there will be, gives us a pH of 1. The pH, interestingly here, is 7 for the second problem, because the H plus from HCl is too small relative to the autoionization. If you do that math, what you'll see is that the autoionization is actually going to be producing more protons than this small amount of hydrochloric acid. You could actually probably drink this hydrochloric acid. You say to a friend, I bet you won't drink 1.0 times 10 to the negative 10th molar hydrochloric acid. And you would drink it without any problems because you actually get more protons out of just plain old water than you would get out of anything else. The pH would be 7. So hopefully that is useful. So now let's get to this slightly more complicated pH of weak acids. So what's the pH of 1.0 molar hydrofluoric acid, where the Ka is 7.2 times 10 to the negative 4th, which just barely makes it a weak acid. And that's why it's because this Ka is very small. It's getting closer to a strong acid. It's not as weak as some of the other acids, but it's still pretty weak. So what are the major species? Well, since hydrofluoric acid only dissociates to a small extent because it's a weak acid, it's not hydrochloric acid or sulfuric acid, what we're going to have as the major species will be HF. So it's not going to be the proton and the anion. Instead, we'll have the non-dissociated HF. All right. So the other major species, of course, is water. So if we ask ourselves, which of these two species can furnish protons? Well, obviously the HF can furnish protons, and we know what the dissociation constant is. It's 7.2 times 10 to the negative fourth. And we know what the dissociation constant of water is. Let me just subscript that water. It's 1.0 times 10 to the negative 14th. So basically, we can ignore the small contribution of protons from water. It's not going to be relevant given the dissociation constant of Ka for hydrofluoric acid. So the pH will be determined by the dissociation constant of HF, and the equilibrium will be Ka equals 7.2 times 10 to the negative fourth, which is the Ka, which is equal to the equilibrium position. The equilibrium position is simply given by the law of mass action. So and these superscripts are a little annoying, so whenever you see that, I try to fix it. But the font on PowerPoint isn't so great. So anyway, here we have the equilibrium position. So the way we do this is, as you may know, with equilibrium positions is these initial concentrations and these final concentrations, and we have to calculate all of this out. So what is the initial concentration? Well, if we know from hydrofluoric acid, they're asking us about a 1 molar solution. So we have 1 mole, right, of hydrofluoric acid, which is down here. Okay. Let's put this here. And then the fluorine, we have, how many fluoride ions do we have? At the beginning of the reaction is 0. And how many protons do we have at the beginning of the reaction? It's 10 to the negative 7th. 10 to the negative 7th. Solving for the Ka requires us to do a bunch of math, and I'm going to explain how I'm doing this math in a second. Let's get to the page. I'll tell you the page that corresponds to this is 666, a lucky number, and 667. So, what are these ion amounts? And so, before any of it dissociates, the proton amount that's sort of curious here is the H plus. So that's 10 to the negative 7th. And we're gonna roughly equate that to 0. I think that's the interesting sort of trick here. So what I'm going to use is this process where I'm going to use the value x, and that value x is going to be sort of this change value. So x is the change in concentration of hydrofluoric acid that we need to achieve equilibrium. So in essence, x will be how many ions will have an equilibrium. It'll be the same number, interestingly. It'll be the same number because it's a change that'll occur. And if that doesn't make sense, just think about it for a minute, because both of these start at 0 in their initial equilibrium, and they end up at x. And what's interesting is the difference on the denominator will go from 1, which is the molar amount, and it'll be subtracted by x. So this change variable will be constant, and this is a pretty neat concept. If you are having difficulty following, I don't blame you, but it's sort of an important method that we will be using for the rest of it. So stay with it for a minute. Maybe I'll try to explain it one more time. So x is the change in concentration of hydrofluoric acid that is required to reach equilibrium, which is important here, since this is the equilibrium position. We're talking about quadratics in a second. This is where it sort of comes in. So some hydrofluoric acid will dissociate to come to equilibrium. We don't know how much it is, right? And that's the question. We know how much hydrofluoric acid we're starting with. That's 1 molar, right? But we don't know how much we're going to end up with. That number is x. So we have x here that's dissociated, and for every proton that's dissociated, there's going to be some fluorine that's dissociated, fluoride. So the x's will be the same amount. And the 1 molar of hydrofluoric acid will decline by however much is dissociated. That should make sense to you. So if we do the math, we're going to get x squared and 1 minus x. Now, how much is going to dissociate? We know how much. It's a very small amount. It's a very, very small amount. So we're going to try to use the quadratic equation in a second, but what's interesting is that the value of x is going to be so tiny that 1 minus x is still going to be very, very, very close to 1, right? So we're just going to call it 1. So the numerator is x squared, the denominator is 1, so basically it's x squared, right? The entire right side of this equation is x squared. And this is sort of a little hard to see, but the Ka we know is given to us at 7.2 times 10 to the negative fourth, and that's going to be equal to x squared. That's the equation. So if we take the square root of both sides, we'll solve everything for x, and x is 2.7 times 10 to the negative second. So this is a very simple way to calculate the values of this, and so we can use the pH, simple pH to calculate this out. So what's the negative log? I guess I skipped that here, but we can do it pretty easily, right? So we take 2.7 times 10 to the negative second. So let's see, 2.7 times 10 to the negative second. Let's take the log first, and then we'll multiply by 2.7. And then if we do the log, and then we negate it, we get 1.5. So pH is 1.56. So this is the Ka, which is, we can convert into pH very easily, and you should be able to do this quite easily. So X, of course, is going to be the amount of hydrogen ions, as well as the amount of fluoride. So pretty simple. All right, so let's talk about very easily and quickly here 14.5. By the way, we're skipping one other weak acid problem, which is very simple, and a mixture of weak acids problem, which is very simple. If you want to do those problems, you're welcome to do them. They're on page 669 in 670, and there's this ICE method that is going to be very useful, and the book teaches that ICE method on 670, and we're going to simply look at percent dissociation, which is a very simple concept where we're taking the amount dissociated divided by the initial concentration multiplying by 100. So we're trying to guess, or really trying to represent what percentage of the weak acid has dissociated. So in this case, in the case of the 2.7 here, 2.7 times something like a second, over 1 molar, this is 2.7% dissociated. And sometimes that's going to be useful if you are in this field quite a bit. All right, so now let's talk about, and then the ICE method is listing the initial and the equilibrium concentrations and the change using X, and we just use this to solve a method, and this ICE method is kind of an easy way to remember how to do these problems. All right, let's go to bases. So remember, Arrhenius, our hero, defined bases as a substance that produces OH ions, but the Brown-Sedlari definition improved that a bit by saying bases are just proton acceptors. So that is interesting. So there are strong acids and there are also strong bases that completely dissociate. Here's sodium hydroxide, potassium hydroxide. These completely dissociate. So you have Na, sodium, and natrium if you like your Latin, and that sodium dissociates from the OH ion. So you have Na plus, the cation, and OH minus, the anion or hydroxide, and this happens all the time. So this strong base, let's calculate the pH. Well, this is going to be pretty easy. The pH of 5.0 times 10 to the negative second molar sodium hydroxide. Well, the major species are the first thing we're going to list. We're going to have Na plus, or cation, hydroxide anion, and water. Well, we know that there's autoionization, but the OH ion is 5.0 times 10 to the negative second, which is vastly more than what we're going to get from autoionization, which is 1 times 10 to the 1 times 10 to the negative seventh. So we're going to ignore the autoionization hydroxide ions. And using the ion product constant Kw, we're just going to have Kw, which we know what that is. It's 1.0 times 10 to the negative 14th, is equal to the amount of protons times hydroxide ions, and we know how many hydroxide ions there are. Now we can rewrite this by dividing OH by both sides. So if we want to solve for protons, we divide OH by both sides, and we're left with protons on the right side, and Kw divided by OH minus on the right side, which is easy to solve because it's just simply 1.0 times 10 to the negative 14th, which is Kw, divided by 5.0 times 10 to the negative second. And if you know a little bit of math, it's very easy to solve as you just subtract the exponents. In this case, you can do some gymnastics to do that. And all you end up getting is 2.0 times 10 to the negative 13th. And if we do the pH of that, just take out our calculator, do negative 13, 10 times 10 to the negative 13th is that, multiply that by 2, take the log, and we get negate the log, and we get 12.7. Page is 12.7, so this is a very basic solution. And that makes sense because it has this, it's a base. It's extremely basic, it's almost as basic as it gets. The only more basic solution would be if it was 1 molar sodium hydroxide. And then of course 10 molar and so forth. All right, let's do some more base work. When bases are dissolved in water, they increase the concentration of OH minus hydroxide because of their reaction with water. How does that work? Well, let's look at ammonia and water, and it reaches this equilibrium where it's ammonium plus hydroxide. So even though ammonia doesn't produce OH, it increases the OH in the solution, which makes it a base. So bases like ammonia that don't have OH groups will typically have a lone pair of electrons, so they'll bond to a proton. When we talk about Lewis definition, it's going to be pretty important. So here's this general reaction. We have a base, B, that's in an aqueous solution. We have water, which will act as the acid in this case. Remember that this amphoteric property, because we had, a while back, we had water acting, where is it? Acting as a base here. So in this case, water will act as, here's my place, as an acid. And then the opposite will occur, where the base will become the conjugate acid. Think of Captain Phillips, I'm the captain now. Now the base says, I'm the acid now. He's been a base his whole life. Now he becomes the acid. He takes over the ship. And in this case, the water, the hydroxide becomes the conjugate base because it wants, it is negatively charged. All right, and they'll battle for that proton the same way that the acids did. All right, so the equilibrium constant is similar. It's Kb is this, the base and the proton on the top. At the equilibrium position, you have the hydroxide ion all over the base. And bases of this type compete with the OH for that proton. So the small values for Kb are weak bases. So ammonium, for instance, has a Kb that's very, very small. And so, for instance, let's take that and try to calculate the pH of 15 molar, that's a lot, solution of ammonia. It's a very weak base, though. So major species are NH3, not dissociated. Remember, because it's a weak base and water, so you're not going to get that dissociated NH3. Both substances can produce OH minus, but we ignore the autoionization because it's so small. So what does that end up looking like? Well, let's add it all up. So we have the NH4 plus, which is what it becomes, right? This ammonium, and then the OH minus from the water. And this is all over this equilibrium position. We know what the Kb is already. So what we solve for is using this ICE method. We have these X's that represent the change. We have the initial concentration, which is 15 molar. And so we have the two X's. And remember, we stay at 15, even though the 15 is changing, right? That 15 molar is the initial concentration. It's the ionized. And the equilibrium concentration, we're still going to be 15 because the X is so small that it's not really going to change the 15. The value is what? It's 1.8 times 10 to the negative fifth. So that 1 minus that is still so close to 1 that we're just going to call it 1. Now the ammonia and hydroxide amounts are X. We don't know what they are. But we know what the dissociation constant for the base is. So we do a little math and we get X squared over 15 equals this number. And I guess if we multiply 15 by both sides and then take the square root, like we did last time, we get this number. And so the pH is 12. So the H plus is derived from the ion product constant. If you didn't follow all of this, just do it over and over again. And I think you'll get comfortable with how it was done. All right, and for reference, this was all done on page 676 and 677. And what's interesting on getting these values for the H plus is we use the KW, the ion product constant. So I think that 2.0 times 10 to the negative 13th and getting this number 6.3 times 10 to the negative 13th was interesting. It's an interesting method at the very least. So getting that kW and then using it to calculate the rest was how we got here. Okay. So this had to be the log amount, so keep that in mind. This is how we solve for the OH amount, right? This made a lot of sense using the Kb, and then we use the ion product constant to get the H+. So as we multiply these two, they will actually equal 10 to the negative 14th. And we get the pH from this amount, not this amount. This would give us the pOH. So we could solve for the pOH immediately from using the equilibrium constant and solving this x squared and rationalizing it. But to get the pH, we had to derive it from the H+ from the ion product constant. So hopefully that made sense. Okay, we're almost done here. Polyprotic acids, say polyproton, right? So polyprotic acids furnish more than one proton. So we have sulfuric acid here, and then we've got phosphoric acid here. Phosphoric acid will give up 3 protons, sulfuric acid will give up 2 protons. Sulfuric acid is the other archetypical, very strong acid. So polyprotic acids dissociate proteins successively, so one after another, and they have different Ka values. So we have Ka1 and Ka2, and you can see that the Ka values become weaker. They become weaker acids as they give off more protons. So the first proton that sulfuric acid gives off is very strong, and it's a strong acid, but the next time it's giving up a proton, it's actually a weak acid, interestingly. So these examples are actually easier than it might be, because we can actually ignore the successive acids because the first acid is the major proton donors in the major species, the same way we ignore autoionization protons, for instance. So sulfuric acid is a little different because it's a strong acid to begin with, and the second acid is a weak acid. So you can read page 683 if you really want to learn how to solve sulfuric acid problems. It's not that difficult and not that different from how we use an ICE table, but there is an exception. You do have to do a little bit of gymnastics that I think is beyond the scope of what we're trying to learn, so I skip it. If you want to learn it, 683, 684, 685, 686, and you'll be home free on how to solve sulfuric acid, polyprotic acid problems. All right, 14.8, we'll talk about the acid-base properties of salts, and this is actually pretty interesting. Now, the book waits until page 686 to define a salt, and a salt is simply an ionic compound, like NaCl, for instance, sodium chloride. So we have salts like that have cations and strong bases like sodium hydroxide, and anions and strong acids like chlorine and hydrochloric acid, and they don't have an effect on pH when dissolved in water. So when you put salt in water, you might ask, you can ask your friends, well, I'm putting some salt in this water, is this changing the pH? And a smarter person who knows all this stuff, I guess, or a knowledgeable person would say no. And we see this in conjugate bases. So conjugate bases of strong acids have no affinity for protons. And this is why this makes sense. If you, again, think about this as a really strong acid, this conjugate base, Cl-, we know it can't compete with water for that proton. It loses that. So it's such a weak conjugate base that it's not going to change the pH. And that's sort of why this happens. If you want to learn the theory of it. So there are all salts that don't produce basic solutions like this, but there are salts that do. So sodium acetate, here's sodium acetate, you can recognize this will become Na+, which won't do anything because of what we just talked about regarding it being a salt, but you do have this acetate ion. So this is acetic acid. So the major species will be sodium, which won't do anything, but you will have acetic acid, or the acetic ion, I should say, and water. So the reaction will be driven by the ion. So the ion, of course, is a base because it's going to want protons. It's going to want H+, as you can see, and water is the proton supplier. So what does this look like? Well, here's the ion, and let me just take a look here, what page we're on, 686 and 687. So the acetate ion will demand the protons from the water, and so here's what it'll look like. And the water, interestingly, right, the water will produce hydroxide ions because the water will furnish the proton over to the acetate ion, and H2O will become OH since one of the H's is skipping town to go to the acetate. So Here you have a creation of OH ions, which is what's making a base. That makes sense. So now this becomes a conjugate acid, or acetic acid is what we recognize it as, which is a weak acid. So the Kb, we want to calculate the Kb. Well, we know what the Ka is. Ka of acetic acid is in every elementary textbook of chemistry. You just look it up. It's 1.8 times 10 to the negative fifth. It's a pretty weak acid. We've looked at similarly weak acids, right? And so determining the Kb is actually really simple because Ka multiplied by Kb has to equal Kw, which makes sense. So this is an easy way to sort of calculate Kb. And now using the equilibrium position, we can kind of do the problems the same way we've done them using the major species and the ice approach. One last thing is there's two kinds of salts that'll produce acidic solutions. One is an example like we just gave, like NH4Cl or ammonium chloride, but there's also salts with highly charged metal ions like this AlCl3. So the book goes into more details if you want to study reactions like that on page 689 and 690. Last thing we'll talk about before, I guess two last things we'll talk about is how the effect of structure on acid-base properties. So how does that work? Why do these things happen? And I love these really theoretical underpinnings of these dynamics. So interestingly, any molecule that has a hydrogen could be an acid, right? I mean, that's a good way to think about acids. But not all of them are. Like if you look at some of these CH bonds, so like benzene, or our favorite CH4, right, methane, and some of these are like some of the other ones. We have what we've got here, chloroform and nitromethane and other methyl-containing groups with these CH bonds are not going to be hydrogen donors. They're not acids. Why? Well, the CH bonds are very strong and they're non-polar, right? Because the electronegativity is so close. But we have an HCl bond. It's actually stronger than a CH bond, but it's very polar because the Cl is so electronegative. So this will furnish that hydrogen ion. That proton will bounce out, whereas it won't in the case of this strong bond CH that's nonpolar. All right. In oxyacids, we have another interesting governing dynamic. So the more oxygens, the more electronegative, and the more easy it destabilizes the OH bond, and the more easily that proton jumps out. And that's a sort of an interesting idea, and I would encourage you to spend some time thinking about why, say, if you have HClO4, HClO3, HClO2, and just HClO, why you get the stronger and stronger acids at the more oxygens you have. And I think you'll see how it makes sense. And of course, it has to do with the bond regarding water. All right. Finally, we'll look at some oxides here. So we've got a situation where we're looking at SO3, and then we're looking at it becoming in water sulfuric acid. So the SO bonds are very strong and the HO bonds are not. So in this situation, you're going to have these very strong SO bonds, and this is a covalent bond, right? So you have the water bond or the OH bond will break and produce protons. So these are acidic oxides because they're covalently bonded. Now you have ionic bonds where you have basic oxides because say with this CaO or K2O, these are ionic. This Ca is a cation, so it'll dissociate, and the oxygen will actually have such a high affinity for protons, there'll be the opposite situation. It'll strip them from H2O, and you'll be left with hydroxide ions. So you have these oxides have interesting basic properties that I think you can work out in your head and enjoy them. And if you need examples, sulfur trioxide and what it's doing to water as a covalent bond, and why these oxygens are going to be stripping off. Right, it'll be stripping off from the water such that you'll be left with H2SO4, sulfuric acid, and then those OH bonds will kick out those protons, and the opposite will happen here. So spend some time thinking about that, and I think you'll enjoy sort of why that all happens. Last slide, very simply, is the Lewis model. So Lewis, this chemist G.N. Lewis in the 1920s, who postulated that Lewis acids is the most general form. So you have the Arrhenius is the least general then you have the Bronsted-Lowry, which is less general, and then or more general, and this is the most general definition of acids and bases. So Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. So if you think about the classic proton as being a Lewis acid, right, and the classic hydroxide being a Lewis base, right, that Lewis base is a electron pair donor, and those electron pairs are coming from the oxygen, whereas the proton is electron pair acceptor. It's very excited to get those electron pairs. So the reason this is interesting, it's very similar to the Bronsted-Lowry model, but the subtlety is to include some more reactions that the Bronsted-Lowry model doesn't account for. So if you take this this very common reaction that the book loves is boron trifluoride and ammonia. Boron trifluoride, interestingly, doesn't have any hydrogen atoms. So thinking of it as an acid could be a little bit difficult, but it is a Lewis acid because it has electron pair. It's an electron pair acceptor. It has room for an electron pair, whereas the ammonia, we know on the nitrogen with its 5 valence electrons, there's 2 that are unbonded. It's a lone pair, and it can donate it to boron trifluoride. So I hope that's helpful. This is the end of the chapter. We're on page 700. It's about a 1,000-page book, so we're about 70% done. The next chapter is again on acid-base equilibria, a little more complicated. We're going to look at buffering and titrations and things like that, but it will really leverage the last 2 chapters. And then we'll head over to chapter 16, which is about solubility and more ion equilibria. So a little bit more math, and then I promise we'll be done with the math when we're going to look at chapter 17 for entropy and energy, spontaneity, do a little electrochemistry, I think, in chapter 18. And then chapter 19, it will be fun to talk about the nucleus and radioactivity, and then ultimately we're done at that point, where chapter 20, 21, and 22 are sort of previews for organic chemistry, and then as promised, we'll get into organic chemistry. So that's really it. I anticipate trying to do these every few days. My life is a little complicated, and I may not be able to keep that schedule, so we'll take a look. As always, you'll see me on Twitter. I hope you enjoyed this, and thank you all so much for joining.